Okay, so today we're going to start on optimization, which is really just a fancy way of saying story problems where you have to find the minimize or maximize value. Okay, now the type of story problems, you will run across so many different types, it's hard to give an example of each one. So you have kind of an approach that you can use to solve these problems. Okay, so we'll just call them guidelines. Okay, so the first thing you want to do is you want to identify everything that was given to you, all the quantities that they gave you just in the description. And make a sketch if it helps. And a lot of times it does help. Okay. So the second thing you want to do is you want to write your primary equation. Okay, and a lot of times your given equation is not your primary equation. You have to actually come up with your primary equation based on what they're asking you for. For the quantity to be minimized or maximized. Okay. Now the third step is you want to reduce the equation that you have for your primary equation. You want to reduce that to a function of one independent variable. So if you have two variables, you want to find some way to make it just have one variable. So you don't want it implicit, you want it actually explicit. And I'll show you what I mean by that in the example. Okay, so if necessary, reduce the equation in step 2 to having one independent variable. And in some cases, it can involve a secondary equation. And I have an example of that also. Bring that up a little bit. Okay, so your fourth step is sometimes it's necessary, sometimes it's not, but I figured I'd put it as a step anyway. Find the domain, which is really just all the values that make sense. And sometimes this is optional. It's just one of those things that sometimes you need it, sometimes you don't, so it's good to have it as a step. Okay. Now, once you do all that, now you want to determine your minimize or maximize value using what we've learned so far, your second derivative test, your first derivative test, things like that. Oh, bring that up some. So determine the minimum and maximum values using techniques we have learned. Uh-oh, forgot the end. So far. Okay, an example of that, either the first or the second derivative test. Critical points, which is just the first derivative equals 0, and etc. and so forth. All right. Okay, so let's say, for example, we have the product is 192, and the sum is a minimum. Find two positive numbers that satisfy these requirements. Okay, so we know we have two numbers that multiply together to give you 192. We want to find the smallest values that will make that true. Well, at least the smallest value when you add them together, that will make that true. Okay. So for your first step, you already know that it's given that the product is 192. So we'll just have x, I'll put given under here, x times y equals 192. Okay. Now your second step, you're looking for your primary equation, which they want to know the minimum, so you're looking for the equation to be minimized. Okay, so you're looking for the minimized sum. So that means your primary equation is x plus y equals, we don't know what it's equal to, so we'll just call it s or l or whatever variable you want. Okay, so our third step is you want to write it as an independent, with one independent variable. So you don't want an x and a y, you want it either just x or just y.
Where did you get x plus y equals 5?
Oh, because we're looking for the two positive numbers that satisfy the sum as a minimum. Yep. All right, so for the third step, independent variables, we have S equals x plus y. Okay? But we also know that x times y equals 192. Which means if we wanted to, we can make that y equals 192 over x. So instead of having two independent variables, we can make this s equals x plus 192 over x. Okay, so where x is our independent variable. Okay, so that's what they meant by the secondary equation sometimes being necessary. We had to use that secondary equation. Okay, so the fourth step, it's optional, but it's always good to know it anyway, and that's your domain. Okay, so we have to find two positive numbers. So really your domain is just x is positive and y is positive. Like I said, not always necessary to put it down there, but it's in some questions it actually makes a big difference. So, okay, now your fifth step, you want to determine your minimize and maximize value. Not just the minimize on this one. Okay, so we just really have to find our first derivative. Okay, so the derivative of s with respect to x is equal to 1. And if we rewrote this, and I'll write it over here, the derivative with respect to x of, let's say 192 times 1 over x. With 192, we can just bring that out. So instead of 1 over x, we'll just make it x to the negative 1 power. Make that a whole lot easier. Okay, so if we use the power rule, we just bring down our negative 1. So 192 times negative 1, and subtract 1. X to the negative 2. So we end up with negative 192 over x squared. Okay, so the derivative of this is just negative 192 over x squared. Okay, so now we have to find our critical point, which is where your first derivative is equal to 0. Which means we have to find where 1 minus 192 over x squared equals 0. Okay, so if we add 192 over x squared to both sides, we get 1 equals 192 over x squared. Clean that up a little bit. And multiply both sides by x squared. So x squared equals 192. Square root both sides. X equals plus or minus square root of 192. But we know from our domain that x has to be positive, so we don't really need the minus. Okay, so we have our x value. Okay, now we know that y from up here is 192 over x. Since y equals 192 over x, 192, if we rewrote that as square root of 192 times square root of 192, square root of 192 times square root of 192 divided by the square root of 192, which is our x value, those cancel out, so you get y equals square root of 192. Okay. So we know that the sum is a minimum when x and y equals square root of 192. Uh-oh.
And this final part, you got y just by taking the derivative of it?
Oh, you mean for y?
Yeah.
Oh, no, for y, we used where we were up there.
Right, we got up there, and then we were able to actually find the minimum for y by just taking the square root of the equation, or by plugging in x.
Yep, just plugging in x.
From the derivative. I see you just split the top.
Oh, no, not the derivative equation, just from our given equation.
Okay.
Yep, that's the equation we were given at the beginning. Yep, our derivative just lets us know where our critical points are. So it's either maximum or minimum. So once we know those, then we just have to find the point right there. Oh. Sum when x is equal to y is equal to the square root of 192. All right. Any other questions on that one? All right. Let's do one more. Well, more than one more, but. Yep, there we go. All right, so let's say, for example, the perimeter of a rectangle is 100 meters. Find the maximum area. We'll clean that up some. So really all that's asking is that if you have a perimeter and if you have a rectangle and you know the perimeter is 100, what's the largest area you could possibly come up with? Okay. So we start with our first step, identify everything that was given to us. And let me see. And me, I always like to start off drawing it so I can visualize. Uh-oh. Okay, so we can have our x sides that are equal and our y sides that are equal. And we know that our perimeter is equal to 100 meters. Okay. So since we know we're talking about a perimeter is equal to x plus y, so 2x plus 2y. Which means we have 2x plus 2y equals 100. Uh-oh, clean that up. All right. So next, we have to find our primary equation. Okay. Now this isn't our primary equation, that's what was given to us. We're actually trying to maximize the area, so that means our primary equation is going to be our area, which is length times width, which is x times y. Because that's what's going to be maximized. Now if we were maximizing the perimeter, this would be our primary equation. So your third step, you want to turn your primary equation to where it just has one independent variable. Right now you're still at 2, you have x and y. Okay, but if you notice, if you have 2x plus 2y equals 100, you subtract 2x from both sides. You have 2y equals, you can say 100 minus 2x. Subtract everything by 2. You have y equals 50 minus x. So that means you can turn a equals x times y into a function with just one independent variable. So that means your area, which is length times width, can now become the area, which is equal to length times 50 minus x. Which, if we go ahead and distribute that, our area is equal to 50 times x minus x squared. Okay. And the fourth step, like I said, it's optional, but it's good to know anyway. That's your domain. And we know since we're looking for a length and a width, it just has to be positive. So we know that x is greater than 0 and y is greater than 0. Okay, now your fifth step is to determine the maximized value. Okay, so first we have to find our critical point. Uh-oh, I'm about to use s again, and that was the last one. Derivative of a with respect to x is equal to derivative of 50 times x is just 50. Derivative of x squared, if we bring down a 2, is minus 2x. We'll bring that up some. There we go. So we know that first derivative equal to 0. Just means 50 minus 2x equal to 0.
Why are we setting it equal to 0?
Oh, because that's our critical point. That's where our slope is equal to 0. So it's going to be either our minimum or maximum, but we know it's our maximum because that's what they're asking for. All right, so if we add 2x to both sides and divide by 2, we end up with x equals 25, which is our critical point. Okay. Now, if you wanted to verify that that's your maximum, all you have to do, which you don't have to, but it's one of those things that's good to know. Remember your second derivative with respect to x. If we take the derivative of your first derivative, that becomes 0, and it becomes negative 2. So whenever your second derivative is negative, you know it's the local maximum. All right, so since we already know that x is equal to 25, if we plug it into this one, we'll be able to solve for our y. So when x is equal to 25, that means y equals 50 minus x becomes y equals 50 minus 25. This means y equals 25. Now, they won't always be equal, just so happens in these two examples they were. But In some cases, they'll turn out to be equal. Okay, so let's say the area, let's say x equals y equals 25. We'll provide the maximum area. Bring that up some. All right, so any questions on that one? All right, leave that up for a little bit.
So it's saying that the maximum area of a rectangle is a square?
Well, just if you know that the perimeter is 100. So if you raise the perimeter,
It'd be different.
yep, it would be different.
So it's got identity issues. Well,
Somewhat.
rectangle wants to be a square.
Pretty much.
Say it.
At least in this case. I think just by the rectangle being 100 for perimeter is the reason why it's equal. So if you made it 200, they would probably be
It's like a
different.
45-degree thing, right?
Yeah.
So then we take first derivative, set it to 0.
Mm-hmm.
Take your critical point, put that in your original equation.
Yep, once you find our critical point, then you just solve for your y value. All right, so this next example, they have different variations of it, but they kind of look the same. Okay, so let's say you have a farmer. Well, I'll wait till after I write it, then reset the timer. Okay, so a farmer plans to fence a rectangular pasture that is adjacent to a river. Okay, now the pasture must contain 180,000 square meters to have enough grass to feed the herd. Okay, so what dimensions would require the least amount of fencing? And that's assuming you won't need any along the river. No fencing is needed along the river.